Hello everyone. So we are about to start this webinar. We are very happy to see so many people here. I see a few people in the chat room here. Hello Harry. Hello Alice. Hello Elio. Who do I know in particular? Lots of nice people from all around the world. So we are probably going to start the webinar in just 1 minute or two to let actually people time to join. In the meantime, what I can say is that there is a chat button on the bottom right of the screen, as well as a questions button where basically you'll be able to ask a question during the webinar, and I think you'll also be able to vote for the best questions. Basically we'll select a few questions at the end of the webinar and try to answer them as much as we can. Yes, let's maybe wait one small minute. I hope you can see the nice view that I have behind me. We are basically hosting this webinar from our Paris office. This is actually the Opera just behind us. So if you ever happen to visit Paris, do come knock at the door. We'll be very happy to walk you through the office and everything we know about speaker diarization. So let me maybe very quickly introduce myself before we start. So I'm Hervé Brodin. I'm the co-founder and CSO at pyannoteAI. And basically today we are 3 people talking with you. So myself, Juan, who is just next to me in the same office.
Yeah, I'm right here. So hello everybody. I'm Juan. I'm co-founder and CTO of pyannoteAI. Glad to be here. Glad to see so many of you. And yeah.
And Thomas, who is not in the same room as us, but joining from the Netherlands.
Yeah, thank you. Yeah, my name is Thomas. I'm an engineer at pyannote. I mostly work on our API and our front ends, and happy to be here as well.
Okay, great. So I think I'll dive right in. So today we are going to talk about streaming diarization, and here is the basically outline of this webinar. First, I'm going to talk about diarization, pyannote, and then how we went from batch to streaming. A few words as well about benchmarking and showing how accurate our new product that we are releasing here today is. And then I'll hand it over to Juan, who is going to talk about the technical side of the API and how we evolved and completely rethought the DIART open source toolkit to end up with this live-1 product. And then Thomas will give a few nice demos of at least one main demo about combining our streaming diarization with STT to make a live subtitling of videos. And then, as I said earlier, so for people who just joined and missed the introduction, feel free to ask questions at the bottom right of this live storm event. And you can also vote here for the best questions that you want answered, and we'll take them at the end of the webinar. So just probably, I'm probably sure that all of you know what speaker diarization is, but just this slide to summarize very briefly what it is. So it's basically the task of answering the question, who speaks when in a conversation, in a multi-speaker conversation, usually with no prior knowledge on the number of speakers involved in the conversation, nor any prior knowledge on the identities of the speaker. So instead of identifying Thomas, Juan, and Hervé, it's the expected output of a speaker diarization is more like anonymous speaker tag, like speaker 0, speaker 1, and speaker 2 in this case, since we are 3 people. Usually, how speaker diarization is addressed is split into 2 steps. The first one is to segment the audio into speech turns, possibly overlapping speech turns. And then a second step of clustering where we group speech turns based on the identity of the speakers. In this example, all the speech turns by speaker 0 are marked as orange, and all the speech turns by speaker 1 are marked as blue. And so a quick overview of what speaker diarization is today at pyannoteAI. So it all started, as you probably know, by the open source toolkit pyannoteAI, and which has become quite popular over the years, though there are just some vanity metrics here. A huge amount of users, lots of downloads on the Hugging Face platform. And so we released a few months back the latest open source speaker diarization pipeline called community-1, that basically on our favorite benchmark called DIHARD III that I'll mention a bit in more details later in the webinar, we reach around 20% diarization error rate. It allows, as any open source software, self-hosting, and we also host it in our own cloud if it's more convenient for you. Then a few months ago, or is it even a year ago? I'm not even sure. We released Precision 2. So it's our flagship speaker diarization model that today serves around more than 200 enterprise customers. We processed millions of hours already. And the main difference between community-1 and Precision 2 is that we reach way better diarization accuracy and also way faster inference. It also comes with lots of bells and whistles, like an on-premise support, the option to extend it with speaker identification, confidence scores, and also our latest product called STT orchestration that I lost my internet connection. Am I back? Thomas, can you confirm I'm back?
Yeah.
At some point, I saw something coming up.
That's okay.
Okay. And so one in the past, actually, so I have right next to me the creator of the diart toolkit. So diart is the streaming extension of the pyannoteAI open source toolkit. So it's based on pyannote models internally, but with specific extensions to make it work in a streaming manner. And so it was released a while back, and we are today with this diart toolkit at around 25% diarization error rate, so slightly worse than the community-1, which is batch, with a 5-second latency. And obviously, what you can see here is that we're missing something. We were missing something, and this is actually the point of this webinar today. I'm going to talk about this missing piece here. So I just wanted to take just one slide to mention a few use cases where streaming speaker diarization is useful and what kind of new use cases it unlocks. I won't go into the details of all of them, but maybe I can, especially since Thomas will show a demo of this one, the subtitling part, so I won't go into the detail here. But for instance, for meeting note takers, one might say that batch speaker diarization is enough, but actually switching to streaming opens up a whole bunch of new features and turning note takers into actual meeting assistants, like assisting people in the meeting during while the meeting is happening. So for instance, thanks to streaming diarization, we can check that all the points in the agenda have been addressed by everyone supposed to talk about them, and maybe trigger an alarm if we reach the end of the meeting without having addressed all those points, or maybe making sure that people actually listen to each other and don't interrupt each other, and that everyone gets a chance to express their opinion during the meeting, and trigger alarms like you might have heard behind me when this happens. Another use case is maybe live logging, where all those wearables and smart glasses might end up recording everyone at any time. So speaker diarization can be used to make sure that people that are being recorded actually gave their consent to be recorded, and maybe like not record when our speaker diarization detects that this or that speaker is speaking. All this kind of stuff, and I'd be very curious to, at the end, maybe in the chat, tell us what is your use case for speaker diarization, for streaming speaker diarization, because we heard a lot about early beta testers of live-1 that we're releasing today, but we'd love to know your use case and what it could unlock. So I just wanted to have a small, let's say, science focus on why going from batch speaker diarization to streaming speaker diarization is not that obvious, and that in fact, even though we use the same word, speaker diarization, those are really two different problems to address. The first thing is that if we focus on the two steps, segmentation that I mentioned earlier and clustering, a part of segmentation is basically detecting speaker change. So I have a small animation here. When we try to do speaker change detection in a batch manner, when we have access to both the past and the future to detect the speaker change, it's actually quite easy to do, because you can compare at a particular point in time what's on the left part of the time and what's on the right. For streaming speaker diarization, we can only afford a very short look ahead time into the future to take the decision. So it makes the problem completely different and way more difficult. Exactly the same issue with clustering, the second part of the pipeline. While batch speaker diarization actually has access to all the here in this video, here in this small animation, each point here actually represents a speaker embedding extracted from each segment here. So in batch manner, you can actually apply clustering in this speaker embedding space with access to all the speaker embeddings. But on the right, when you do that in streaming, you only have access at speaker embedding up to the point where the conversation is currently. And that makes the problem much more ambiguous. And it takes some time, as you can see here in the demo, to actually figure out whether two speakers are, two speaker embeddings are actually belonging to the same cluster, or if you should detect a new speaker. So that really explains why going from batch to streaming diarization is a completely different problem. So I'm very happy today to announce the general availability of live-1. So we have a bunch of beta testers that have been using it for the last months. And thanks to their feedback, we managed to improve it even more during this beta period. And so we're very happy to announce that today, live-1 is actually better than our open source batch community-1 diarization, and with an extremely low latency of 300 milliseconds. And so this was a lot of work. I'd like to take this opportunity to basically thank all the members of the team who did an amazing work at combining the work on the research side and the tech side to make things work very nicely and reach this very low diarization error rate on DIHARD III, which is really, I think, the most representative benchmark that we can use today to evaluate speaker diarization. So contrary to DIART, which only supports self-hosting, we serve live-1 on our cloud. It's available today. I'll show you that right after. And it allows also multiple streams to be processed in parallel, while it's kind of tricky to do that with the open source toolkit. So a few words about benchmark. So I had, with lots of requests from the internal team at pyannote, I had to do a meme once again in all the webinars. So here it is. Where are we? There we are. The point of this slide is really to show that there's lots of benchmark about speech to text around here, but most of them are actually focusing on single speaker recordings. And most of them are also focusing on batch transcription. Here at pyannoteAI, we focus on multi-speaker recordings with lots of overlapping speech, as in any real conversation. And we both evaluate our diarization in batch and streaming, and our benchmark are available at pyannote.ai/benchmark, as shown here. So a quick comparison with some providers that also addresses streaming speaker diarization in their product on DIHARD III. So here, DIHARD III is basically a data set contained of 11 different sub-data sets. So it's a compound data set with very different types of conversations, from a two-speaker phone conversation to conversation between friends in restaurants with noisy backgrounds and everything. And so you can learn a bit more on our benchmark page about what DIHARD is about. But basically, the learning here is that we reach less than 20% on DIHARD 3. And you can see here the split into the 3 types of errors that a diarization system can make. It can make false alarms when it detects speech while there shouldn't be speech. It can make speaker confusion when it confuses speakers. And it can make misdetection. And misdetection can be coming from 2 different errors. The first one is when there's the system outputs a speaker while actually no one is speaking. But the most important, and we think about that a lot at pyannoteAI, is the missed overlapping speech. While here at pyannoteAI, we really think that overlapping speech should be really handled. Most of our competitors, if not all, don't even bother trying to detect overlapping speech, and that explains, I think, the high misdetection for them. So without further ado, I'm going to do a quick demo with Juan, who's here. So we are in the same room here. So I'm going to switch to the playground that you can access today if you create an account on pyannote.ai. So sharing the playground. Here we go. Okay. So I'm going. So as you see, basically when you log on dashboard.pyannote.ai, you have this streaming playground that you can go to. And then what I'm going to do is that I'm going to click Start Talking. And basically, so you see, I'm apparently speaker 0, and I'm soon going to hand over the presentation to Juan.
Yeah, so if you can see the latency, it's actually responding pretty fast.
And I can actually overlap.
You shouldn't interrupt me. I have so much. You should.
I really apologize, but the point was to show that we're very good at overlapping speech detection.
I mean, we really are.
Okay, so you get the idea. You can actually play with the streaming speaker diarization with your microphone on your laptop as soon as today. So I'm going to now go back to the presentation and switch to the part by Juan. There we go.
All right. Thanks, Hervé, for this cool introduction. So yeah, I'm going to talk a bit more about the technical details of live-1. So you just got the introduction about the science part, the context about pyannote, and what live-1 actually is in terms of accuracy and a bit of speed as well. Plus the demo, which is, I mean, the bar is really high right now. But yeah, so if I can give you a quick overview of what live-1 is in terms of what it can do. So we have a 300 milliseconds diarization latency, and that's including the network. So that's total latency time. We support actually 100 millisecond chunks at 16 kilohertz at the moment, and up to 8 speakers. And per team, there's only a limitation of 10 parallel streams. But we have, you can also have audio of up to 5 hours, and you get from a WebSocket API. So from the same WebSocket connection, you send audio, and you receive speaker diarization events. So that would be the start time when a speaker starts talking alongside the speaker label, plus another event saying when that speaker ends talking with the speaker label and the timestamp. And all of this is, as I said, exposed as a WebSocket API, so it's easy to integrate with any current established AI and voice AI pipelines. So to dive a little bit deeper into how that actually works from a user perspective. So there's the usual API that you might already know from us, which is api.pyannoteAI. What one needs to do to create a new stream is to send a post request to v1 live. That gives you a response, as Thomas will mention in a bit, the WebSocket URL to which you need to connect. And so that WebSocket URL is actually pointing to an orchestrator, a session orchestrator that's deployed on Cloudflare. And within that WebSocket connection, you can send the 100 milliseconds audio chunks, and you will receive the events back in the same connection. So a speaker has started speaking, a speaker has stopped speaking, and so on and so forth. But behind the scenes, this is simply an orchestration layer. What the orchestrator does is it establishes session tunnels with GPU workers. As I mentioned, there were two parts of the speaker diarization problem, segmentation and clustering. So there are two different workers for each of those that scale independently, and they each share different orchestrators for different connections. So this is something that can actually scale quite easily. And the orchestration and the passing of messages between one worker to the other is handled entirely by the orchestrator, as well as sending back the events back to the user to notify of diarization events. And these workers are actually deployed in a GPU inference platform that's called Modal, not to confuse with Model. But yeah, this is the way that the live-1 infrastructure works. And so, to contrast a bit with what exists or existed before in the open source speaker diarization community, as I've mentioned, I'm the creator of a library called DIART that adapts models from pyannote to the real-time use case. But there was always a problem that we heard from the community with DIART, which was about the scaling and about the model communication, the fact that you need to fine-tune these pipelines in very specific ways, depending on the audio domain. So it wasn't very easy for the community to actually self-host and deploy these models because of all the complexity. But as you can see, you can see in this diagram that represents the way that DIART works, the different components that we just mentioned. So speaker segmentation, speaker embedding, and clustering, except that they are, as I mentioned, tightly coupled, and so it's difficult to scale them on their own. So just to compare a bit that approach with the new live-1, we decided to actually take a step back and rethink this problem from a truly streaming perspective. So as I mentioned, DIART deals with models that have been trained for batch, and so for high latency. In the case of DIART, that's 5 seconds. And live-1 has actually been designed from the very beginning for extremely low latency. As you have seen, it's 100 millisecond chunks and 300 millisecond total latency. So that's for the most the hardest use cases that require the faster response times. And another problem that we had with DIART regarding the GPU execution part was the fact that we compute we do inference on the same audio many times because of the overlapping chunks that DIART requires to actually get a nice average of the diarization from different perspectives, let's say, of the same audio. That was quite wasteful, and it was, well, in a world where GPU inference is so costly, it's something that we thought we needed to address before actually scaling that better. So live-1 is actually working with 100 millisecond non-overlapping chunks. And we can actually perform inference at that time step. So scaling workers is way more complex in DIART than it is in live-1 because of this approach. But something that's sometimes a bit forgotten, but is actually quite a barrier to deploying this in actual production applications, is the need in DIART to tune hyperparameters for specific domains. The 25% DR that Ella just mentioned is actually with a carefully tuned set of hyperparameters. that live-1 doesn't have. So again, from the very beginning, we decided that we wanted to get rid of this limitation, and we did. So the live-1 that is available to anybody on our API actually doesn't need to tune any hyperparameter. So it's, again, way easier to adapt and to deploy in production scenarios. And one last thing that I should mention is that the output of DIHARD was actually quite verbose and noisy, because at each, I think it was 500 milliseconds, you get an entire block of diarization with their own start and end timestamps, with different speaker turns and all that. And so that sometimes is quite hard to parse and to use from the perspective of our clients and of our users. So in live-1, we decided to go with a more event-driven output. So in this case, you just receive the event notifications for those events that are actually worth listening to. So that is when a speaker starts, when another one ends. And this also nicely handles overlap, because it's a matter of, well, each of the speaker turns timestamps are kind of independent. So this is something that we can absolutely handle there. So that's it on my end. But with all of this, I will leave you in the good hands of Thomas, who will be showing you how this all works in a real use case of subtitling.
Yeah, thank you, Juan. Yeah, so I'll be doing a demo of a subtitling system. Yeah, thank you, Hervé, for the next slide. Yeah, so it's a pretty simple system. We're going to connect to our streaming diarization API, of course. And we're going to work together with the OpenAI real-time API for transcription. And then the idea is that we're going to combine this to have one speaker attributed subtitle, and then stream that back to a front end in the browser to actually display speaker labels on top of a video. And we'll share the code, of course, in a public repository in GitHub. You can find some of our previous tutorials as well, and you can get a deeper dive into the code. Yeah, go ahead to the next slide, please. Thank you. Yeah, so this is a basic architecture overview. The tech stack is, we'll use TypeScript, and we have a Bun and Hono-based server. This will basically receive the audio chunks from the front end, from the client, and then stream that to our API for diarization, and also to the real-time API of OpenAI to get the transcription, and then send that back to the client side. And it's really just an abstraction, so the browser doesn't care what API you're using. It just receives those subtitles with speaker labels. And yeah, we'll use the SDK from OpenAI, and we'll use our own API, of course, as well. So you need an API key for both the providers. You need have Bun installed on your machine to test this. You need a browser. And we'll use a pre-recorded video file right now, just to have some control over this demo, but you could easily swap this out for an actual stream of audio from a microphone or some other type of stream. So yeah, so we'll just use this video file, but you can swap that out. So I'll now share my screen to show you what it looks like, and I'll show you a demo of it. So let me do this right now. We'll start my local server. So yeah, this is the video player inside of a browser. And as soon as you can see actually in the bottom right, there's a status label. So you can see the status of our API, and we send this to the client side as well. And as soon as I hit play on this video, we'll start initializing both of the APIs. And then once they're ready, we're going to send chunks of audio. And then you'll see, so there's maybe like a second or delay before you actually see the subtitles on the screen, but they will show up, and then you can see like the actual live subtitles of this video. So I'll just show you this short clip, and then we'll dive into the code a bit to see how it works.
Satiated on those robots, then it's a very different story. Yeah,
right. But now we're talking about the consumption world, whereas for the investment side of things, there could be just some greedy titan of industry who keeps wanting more and more robots. And that alone would be enough.
It would.
To increase the marginal value of robots and therefore decrease labor share?
Yes.
Yeah. Okay. But why are we not expecting greedy titans of industry to keep existing?
I mean, greedy titans of industry historically have like built library.
Okay, so that was the short demo. You could see the transcript chunks and the speaker labels being streamed to the client. So let's go a bit over the components of the code of this demo. So yeah, the first part is really just in the browser side, you load this video file, which again can be a microphone or anything. And we use relatively modern browser feature called a worklet to get that audio stream separately from the UI thread. And this is just to make sure it doesn't block the actual rendering of the things that you see on screen. And then, so we use that worklet to get the actual audio. And then we downsample it and we create frames of 100 milliseconds. And this is just because our API expects this, our diarization API expects this shape of the data. And then we send this to the server side of this application, which is the next step. So actually, these steps kind of go at the same time. When you hit play, we initialize the streams. So for us, you can see our API with a simple HTTP call to get the WebSocket URL. And for OpenAI, we use their SDK. We wait for both of them to be ready. And we send that back to the browser side, basically as a signal to say like, hey, you can start sending the actual audio chunks. And then back on the server side where we receive the chunks, we can just send them almost directly to our streaming diarization API. And OpenAI wants a slightly different format and a slightly different sample rate. So we have to resample this. And you'll find this across other STT providers, like every STT provider, transcription provider has a slightly different requirement for the sample rate and chunk size. So yeah, you always likely right now have to do some resampling, but typically that's okay. You could see in the demo like it was still pretty fast with returning the results. So yeah, that's the next step. You receive the speaker turns. The data is you get the speaker label, the timestamp, and whether it's a start or an end of the turn. And this is also the part where it gets a bit complicated because, like we've mentioned before, we can actually detect the overlapping speech, but a transcript is usually from one of the speakers. So we just assign, we keep track of the current active speakers if there are multiple, and we try to assign it to the right transcript segment. Another thing to note here as well is that at the end of a speaker turn, we commit the current buffer of audio samples to the OpenAI transcription API. And this is because, and you'll find this in the other STT providers as well, they send a partial transcript, which is sort of the initial one, and then a final transcript, which can be slightly more accurate. So depending on your use case, you might want to only use the partial if you're really going to get, if you really want the lowest latency. If you want slightly more accurate, you can use the just wait for the final transcript chunk. And that, yeah, kind of depends what exactly you want to do. Yeah, and then for the next step, one of the last steps, thank you. So yeah, we assign the labels that we receive from our diarization API to the transcript segments. And then we wait till the end. And if there's some overlapping speech, we decide whether it's like the whole segment or just a small interjection. And if it's just a small part, then we just leave the main segment as like the initial speaker, and we don't swap that out. And then, yeah, we simply stream that back to the browser side, to the client side with the events, the actual speaker label and the text. And then, yeah, the browser renders this. We added some colors and overlaying this on top of the video to show this. And we've got a lot of feedback during the beta on reconciling these subtitles or reconciling segments and speaker labels. So I think we'll do some more investigation about what's the optimal way to do this, especially across multiple STT providers. We're still figuring out what's the best way. There are so many possibilities, and it kind of depends on your exact use case. So yeah, we'll definitely get back to that. So yeah, this demo is just a start. You can of course swap it out with another STT provider if you like. You can swap it out and use your microphone as input or some other type of audio stream. And of course, obvious thing to think about. You can throw these the transcript segments to an LLM to get translations. You get live translated subtitles, or go for more challenging use case as well, where you not only translate, but you also do voice cloning and text-to-speech to get live dubbing. And yeah, as we talked about before, you can have the AI note taker or like a AI meeting assistant. For example, you could periodically send the transcript with the speaker labels to some LLM to get some notes, or some other maybe action items or something. And yeah, this demo is really the start of this. You can build things on top of it. That's the idea. You can swap things out. And of course, this is just a browser and server-based application, but you could build something. Our API is just WebSockets and HTTP API. So yeah, you could build a desktop application as well, maybe in Rust or something. And again, I invite you definitely to take a look at our code of this demo on the tutorials repository on our GitHub. To have a deeper dive into this as well. And I think that's it for this demo.
Thank you, Thomas. So we were not bit by the demo effect, so that's great. It all worked as expected, but we were confident. So we now reached the end of this webinar. So I'm just putting here a few links for you to try. So basically the playground that we showed earlier, this is where you can create an account and get some free credits to play with the streaming diarization as well as the badge diarization. So the code of this demo is already available in this GitHub repo. And then obviously you can look at the documentation to learn more about how to use the API. And feel free to join us on Discord or keep up to speed with what we're up to on X. So as Thomas was saying, I'm really looking forward to the use case that you have in mind, and now we are going to go over the questions. So I'm just discovering the question because I was focusing on the presentation.
I've been already answering some of them.
Okay. Do you want to maybe take one in particular?
Let's maybe look at the votes.
Votes, yes, votes. Can we sort them by votes? I see one I think that is directed to me in particular about research problems that you think I guess are still left to solve. Also, the domain of the speech is becoming overcrowded day by day, but still there are problems which are not taking the attention of the researchers. So I've been working on speaker diarization for the last 12 years or so, really focusing on this problem. And as you can see, it's still far from being a solved problem. So there are many reasons why we still fail in some difficult cases for speaker diarization. So really, the first thing comes from the fact that we really have no prior knowledge about the speakers involved, about their numbers, and really estimating correctly the number of speakers is really a problem that needs to be that still remains to be solved. We are getting better day after day, but this particular part is the kind of feedback that we might have, that sometimes there's a few speech turns here and there that remain assigned to a speaker that they shouldn't be, and so basically reducing the confusion in the if I go back to the benchmark here, let me go back here on what remains to be done. So even though speaker confusion doesn't necessarily seem to be where we make most mistakes, this is the kind of mistakes that user of the technology actually really feel and witness at first time. So we really need to focus on this speaker confusion part. And obviously, so we managed to reach a very low latency, but it's at the expense of accuracy. So maybe finding ways to improve the trade-off between accuracy and latency is something that we need to focus on, in particular for speaker diarization. And if I go to a bit further, so speaker diarization is usually not the final goal. Speaker attributed transcription sometimes is, and so improving speech transcription on overlapping speech in particular is something that is really not solved. Most of the speech-to-text model are trained on single speaker, therefore non-overlapping speech, and they fail miserably when they are overlapping speech. So that's why on our roadmap, we have this, we not only on our roadmap, but internally, we've been working a lot on the separation side of things. So one audio in, multiple audio out with only one speaker per audio, even on overlapping speech regions. So I think this is where we're going. Is there another questions that we should?
I think there's an interesting one here at the end that has 3 upvotes. So it says, if I use the streaming diarization API for the translation function and the outdoor environment is very noisy, and there are many people speaking around me, could it still work well? Can it recognize who I am and who the right person I'm talking to is? I think that's kind of where we shine, actually, the difficult scenarios with lots of noise and lots of overlapping speech, maybe babbling noise. Actually, the numbers that we report here on DIHARD III are one of the most difficult, if not the most difficult, diarization benchmark out there.
Public diarization benchmark, I'd say.
Yeah. So yeah, I think it would be very hard to do better than us on that front.
Thomas, you raised your
hand. I wanted to add to that our streaming playground also works on your phone. So you can, of course, just try this out yourself, take your phone outside, turn on the microphone, go to your browser, and go to the playground, and definitely report back to us what your finding is. But it should be decent.
I think also I've seen 2 questions related to the cold start problem or the warm-up time of our streaming diarization, both on the model side and on the architecture side. And so one of them was by Harry, I think, if there's a potential cold start to request to the WebSocket of live-1, and there's another one by where did I see? Ki Yoon. The question is, in real-time speaker diarization, I assume the cold start phase at the beginning of a conversation has the highest diarization error rate since there is little speaker information available yet. How is this actually handled or mitigated in practice? So do you want to answer on the text side of things, and I will answer on the other part?
Yeah, I think I kind of answered partially there, but so on the modal front, there can indeed be some rare cases where we need to scale up because we cannot have all the different GPUs available at the same time. So that might be rare that you run into an upscale scenario and there's a short 5 to 10 seconds cold start. But in general, that hasn't arrived much. And gotta say, once the connection is open and you can start sending audio, because the API also asks to wait for the orchestrator to actually be ready before you can send audio. Once that's there, then you actually retrieve those 30 millisecond numbers for total latency.
Thanks. And on the accuracy side of things about the higher or not errors at the beginning of a conversation, actually, what I can say is that you'll get the best diarization out there from pyannoteAI, but it's true that it might take a few seconds, not necessarily at the beginning of the conversation, but the first time one speaker speaks to actually get that speaker right. I'm talking about 3-4 seconds, but this is something that we are currently aware of. We just got out of beta, and it also this beta period of 1 month already allowed us to go from actually, I think the first release that we put in the hands of customers of beta testers were around 23% or 25% for DIARD, and we are now below 20, and we are still working very hard to reduce this number even more, and in particular on this case where the time it takes to actually detect the first time a speaker starts speaking. But later in the conversation, there's no issue at all, but the very first time they speak, it might take a few seconds before getting them right. Maybe I see that we schedule a 45 minutes time for this webinar, so we reach almost the end, but is there another question that we could
I
take?
think there's an interesting one. The talk with 3 uploads. Can it run on the device side? So I guess it means on device, like smart glasses, for example. Well, at the moment, we're only exposing this as an API. So as long as the smart glasses have an internet connection, I guess it would work. Yeah, we're working on improving this and bringing to other modalities as well. So in the future, I think it will. It's something that we'll be able to run on device.
Okay. Well, I think we answered most of the questions that we got. Thank you very much for being so many attending this webinar. So all of you who registered will, I think, receive the recording in the coming, I don't know, days probably. And so looking forward to what you're up to, playing with our streaming speaker diarization, and yeah, have a nice summer, and see you soon. Bye.
Thank you, guys.
Everybody.
Bye-bye.
Bye-bye.